Professor Gábor Szabó, member of the Hungarian Academy of Sciences, rector of this university, but I don't think he's going to focus on this capacity, but he's going to tell us about the lasers, the history of lasers in Szeged, on which he has been sort of an integral part and an influential figure. And I should like to thank him for coming here and giving us this talk. Thank you very much.
Thank you very much and good afternoon. Really, if you are a rector of a university like ours, then you could be an expert of medieval stamps or something, which might not be very well suited to the topics of this conference, but I happen to be a laser physicist. And what I will try to present you is, in a certain way, the history of the laser activities at the University of Szeged, and actually I will try to present it in such a way that there might be some lessons to be learned. First of all, I will start with the early days, even actually with days when I was not yet present here. This was the very first laser operation in our laboratories. You should know that the classical fluorescence spectroscopy was a topic for the department for decades. So the very natural idea that in 1967, when the dye lasers were invented, then of course right after that our colleagues tried to reproduce the dye lasers. Dye lasers were very important for the next quite a few years. Actually, see what you see here is a good example of laser physics behind the iron curtain, because this laboratory is not only ugly, but you see that there are basically exclusively Soviet instruments, because at that time, of course, we had the embargo, and nothing that was fast, nothing that was for high power was available. So it basically, we had to do, I will come back to this in a minute, many equipments we could not buy, we had to develop it for ourselves. So these were actually mostly young colleagues at that time. Some of them were actually professors of mine. Then, when I joined as a student the laboratory, Gábor, who was a defining member of the laser activity Szeged, was already present. And actually, this is what I mentioned before, that we wanted to study dye lasers. You could actually best operate dye lasers by pumping it with other near-UV pulse lasers like nitrogen lasers. So in other countries, you would have gone to the shop and buy a nitrogen laser. In Hungary, we had to develop it for our own first. So before studying dye lasers, we developed the nitrogen laser in order to pump the dye laser. You see that this is actually pretty much homemade. It looks like it is made in a garage shop, and actually it was made in a garage shop, in fact. But then there were some scientific advances. The early scientific results, mainly we tried to simulate the temporal behavior of the lasers. These lasers had funny temporal oscillations, and it was quite important because at that time people started to realize that short pulse lasers can be used for many scientific applications. And then Gábor, okay, these are some other lasers that we have developed, and we actually even sold these lasers, and thereby we got money for our research. This is a low pressure nitrogen laser. This is a dye laser. This is a dye laser head. pretty short. It was useful for some applications immediately. Then, of course, we also developed our excimer laser, because this was what you have seen in the literature, that excimer lasers are very useful and handy. And we have developed our excimer laser as well. But then, actually, we already headed towards ultra-fast science. There were two breakthroughs which actually Gábor in Göttingen has achieved. First, he realized a new phenomenon in the distributed feedback dye lasers. These are dye lasers made in a tricky way. Distributed feedback means that you don't have two mirrors around your lasers, but you have a periodic structure, which is a distributed mirror, because it acts like a crystal that a certain direction it will reflect. So basically the trick here is that you try to make an ideal interference pattern. I will come back to this because this is an idea that came up several times later on. But then these lasers show an interesting phenomenon. You see, this is a nitrogen laser pump distributed feedback dye laser that generates 60 picosecond pulses. So you can use these lasers to generate something like a couple of tenths of picoseconds. This was pretty good at that time. The shortest pulses were in the order of 10 picoseconds, so it was quite close. Then the second is that Gábor has developed a very, very nice setup how to make perfect interference pattern using a non-perfect laser. The trick here is that you take a diffraction grating. The laser falls on the diffraction grating, then you have the two orders of diffraction, and these are combined on the surface of the dye cell, and this here is simply a rectangular silica block. So it's a very easy laser, but it has the very interesting property that it creates an almost ideal interference pattern here, even if the laser is not really coherent. If you think about it, the trick is that if you change the wavelength of the laser, then the diffraction angle changes. If, say, you increase the wavelength, then it will be broader. But then it will meet on the appropriate angle. So basically, the angle here, which creates the interference pattern, changes proportional to the wavelengths, which actually means that each and every wavelength here does the same interference pattern. So these two breakthroughs led to dye lasers and wire dye lasers to short pulse, to larger pulse science. And you see here the advantage of this distributed feedback dye laser, because here is the grating, here is the quartz block that I mentioned, and here is the dye in the event. And you see that it is very easy to change the wavelengths of the dye laser simply by changing the dye. So you can have red, green, and blue. It was very advanced at that time. This was one of the best ways to generate short pulses. Then we eventually developed a dye laser system in an oscillator amplifier arrangement where we actually could generate 300 femtosecond pulses, 150 microjoules at blue wavelengths. This was at that time a pretty useful light source. We have, of course, immediately tried to do some applications. This we have done this measurement with our colleagues at the Biological Research Center, and these were actually the fastest biological signal for almost 10 years that people have measured, because this is the charge separation signal of still, this fast component was not known before. It was a pretty interesting story. People wanted to use it as electronic switch, for instance, and theoretically it could have been possible. But then, 10 years later, practically, we have tried to use the same interference, the same method to generate perfect interference pattern to make very narrow lines on polyimide. This is actually a step towards microelectronics, towards a high resolution photolithography. The idea, we have done this experiment in Houston. This was actually the first encounter with microlithography. I will try to show you that once you understand something, then you may use it in several ways. This was pretty much, I mean, this whole distributed feedback dye laser story was when we started to understand what light does when you have a very high density interference. And this was a natural idea to try to go towards photolithography. Here are the results. These are the lines that we have actually generated in polyimide, which is still a very important photoresist in microlithography. Then we have moved towards high power lasers. We had already short pulse lasers. And then we had excimer lasers by which you can amplify the energy of the laser pulse. As you see here, half a picosecond and 50 millijoule, which is actually close to a terawatt. So this is a pretty high power laser. Professor Szatmári has developed this setup in 84 in Göttingen. Then I also developed another terawatt class laser in Houston. This guy here has already quarter of a joule energy, 250 femtoseconds. And the focused intensity that we could achieve was 10 to the 18th watts per square meter. This was pretty high at that time. Actually, just to imagine what does it mean? You have 10 to the 18th watts per square centimeter. You can imagine that you have a lens by which you can focus the sunlight into a millimeter, a spot with a diameter of a millimeter, then you have 10 to the 18th watts per square centimeter. So it's a pretty high intensity. This is actually the threshold where the so-called relativistic optics starts. This is the threshold where, for instance, single electrons start to behave funny when they interact with these very high intensity laser fields. In any case, this is something that was quite interesting at that time. Since then, it is a very important field of research. There are two laboratories now in the institute, the high intensity laser laboratory, Professor Szatmári. Here you have UV lasers in the terawatt range, and then of course the terawatt titanium sapphire laser, the laboratory of which was originally developed by Gábor Szabó, and this is a multi-terawatt laser. Here the focused intensities are already in the 10 to the 19th watts per square centimeter range, or luckily above. We, of course, try to do applications. I have already shown you by application, but then we started to investigate in the early 90s laser ablation. These are photographs that were done to understand how photoablation takes place when you use UV laser to shape the cornea. These are big corneas, and these are the shock waves that are generated by the photoablation process. And so we had a line of research which actually is still going on. Our colleagues, first of all, Professor Béla Hopp, is still working in several aspects of photoablation. This was quite an interesting time because these were pretty much the early phase of photoablation, which actually was paving the way to eye surgery with excimer lasers. Then we also did some high-resolution photolithography. The reason why I'm showing you this actually, this is a page of my lab book in Houston. It was, I think, we had 92. It was 92. We had a group meeting. I proposed an idea. My boss, Frank Tittel, immediately told me, okay, fine, it's a new idea. We have to go immediately to the notary public to get the page of the lab book notarized, because that was the time. I don't know whether you heard about the 30 years patent war of laser physics. So in 59, Gordon Gould practically has made a drawing of a laser. There was no operational laser, but he has made a drawing in his lab book. He got it notarized, that it was officially witnessed that he had it, and then he filed for a patent, which was rejected. Then a year later, people have actually made the laser, and then Gordon Gould was fighting for 30 years to get his patent valid, and for his luck, this happened 30 years later. The reason why he was so lucky is that if he had his patent immediately accepted, then after 20 years, it is game over, so there is no royalty anymore. But from 59, the next 20 years, there were practically no laser market. But he did not get the patent only in the end of the 80s, where there was a huge laser market. And then the 20 years for him started. So basically, he had made much bigger income on royalties that he was not immediately, his patent was not immediately accepted. And actually, this whole story was about the drawing in his lab book, and that time people were very aware of that. So my boss immediately thought that, okay, fine, we have to, it made no sense. Since then, we actually filed for a patent, we got it immediately, so there was no need to get this page of my lab book. It just mirrors the spirit of the early 90s. There was, of course, a very, very fast expanding laser market. People were pretty kind of conscious about such things. And then, a very good student of mine, called Miklós Erdélyi, joined me in Houston, and he actually has made the first experiments with that arrangement. This is actually an arrangement by which you can make half the period of the light. Basically, this is something by which you can kind of take the wave nature of light out, at least for a factor of 2. This was pretty much also the time when we started to understand optics. This is the reason why I'm showing you this figure. This I was his master's thesis advisor. I had a jolly good idea with a biofusion pistol. The idea unfortunately never worked, but Miklos has learned how to deal with pistol optics. And a year ago or so was your last publication by using biofusion plate. So once you learn and understand something, you never know when it becomes useful. It's really a pity that it was such a nice idea with this biofusion pistol for a third order compressor for short passes, but unfortunately it really never worked. In any case, that's how science develops. Then let's go towards current topics. What we are doing. One current topic was these two terawatt laser laboratories with many different applications. Actually, we have, of course, our colleagues are still working with many different applications of laser ablation, especially Professor Hock and his co-workers have developed several tricks how to make some microtechnology. Micro in this case means submicron, possibly 0.1 micron technology, especially with transparent media, because transparent media is in many ways not that easy to work when you use lasers. So this is a still ongoing topic with many different applications, and of course some plans for the future as well. Then of course we, from early on, try to use lasers for medical purposes. This is a joint project with the colleagues from the clinics of the dermatology. Psoriasis is a very nasty, not quite disease, because practically it's harmless, but it's not very nice, and therefore those who have it don't like it, of course. And of course it was known that psoriasis can be treated with light, especially with near UV light. The problem is, of course, that when you are using light, then your skin might not be so happy. So the trick here was very simple. We realized that the wavelengths of the xenon chloride excimer laser is practically almost the optimum, and therefore we have demonstrated that using excimer lasers you can make phototherapy by using doses factor of 5 or 6 less than earlier, which is quite a big difference when you are speaking about UV light. Then we had some other applications as well. We have developed a phototherapy for hay fever as well. Then of course, as I mentioned, once you try to understand optics, then of course it is a challenge to try to do something that is better than the wave ratio of light. This was actually the most indirect step towards the current high resolution microscopy. We made the bad mistake. We have developed a setup that we demonstrated that it has an approximately 40% better resolution than the wavelength limit. But we made the bad mistake that we have published in a physics journal, and nobody cared. We should have published it with some stupid biological stencil, and it could have been that the response would have been quite different, because of course the problem is, or the story is, that if you tell a physicist that I can have a bit better or somewhat clearly better resolution than the wavelength of the light, don't you take an electron microscope? If you tell the same as a biologist, he would definitely know the difference between electron microscope and optical microscope. So actually the optical methods have their value practically excluded in biology. That was a lesson that we have learned the hard way, because it's really a pity, because it was, in my opinion, quite a neat trick at that time, but still we did not give up. And I think you have seen the laboratory of Miklos, who is now leading the advanced microscopy laboratory. But this was pretty much the forerunner of that story. This is the actual image taken by, this is a tomographic optical microscope. Of course, it's not that easy to see, but if you really have a closer look at it, it turns out that it is approximately 40%. It has approximately a resolution that is 40% better than the normal confocal microscope. Then I would like to, since I have learned that the microscopy story will be presented to you, I will spend a bit more time on other areas where we are active, because as far as I understand, there was no talk about that topic during the course. So basically, we have had another look at a technique that was almost forgotten in the early 90s. In the late 70s, early 80s, it was the number of articles were actually really growing. Photoacoustic technology means simply that you take presumably a laser beam, send through the sample, and modulate it. Imagine that you have this laser beam which is tuned to the absorption of a species in the sample that you are interested in. Now you turn on and off your laser, which means you deposit energy in the gas, and then you switch it off. This means that you make a periodic temperature modulation. If the temperature modulation is fast enough that the gas cannot expand, it simply means that you are working in the kilohertz regime, then you have a temporal modulation and the gas cannot expand. So what happens? The pressure will be modulated accordingly. Modulated pressure at a kilohertz range has a very well-known name, it is sound. So basically then you take a microphone and detect this sound. The sound, of course, the intensity of the sound will be proportional to the laser intensity, to the absorption strengths of the species, and of course to the number of molecules, of the concentration of your analyte. If you think that it is not a very good idea to turn the absorbed laser energy into sound, then I propose you to think about it, because it turns out that sound can be very, very sensitively detected. Imagine 60 decibel is a pity. It is a sound which is not yet hurting, but it is pretty loud, so you normally, after a while, you would like to have a bit less than that. But if you consider the pressure modulation in sound that is 60 decibel, then it corresponds to 2 centimeters of air. So basically, when you do this, then you have a 120 decibel sound in your ears, which should of course drive you crazy if your brain would not be able to get rid of it. So in sound you have a very slight modulation of pressure, and you can very sensitively detect sound, and this is why it is worthwhile to try to turn the absorbed energy into sound. So this is this was the basic setup for photoacoustic, and starting from this point we have been actually the trick is that you can use this whole thing is very robust. This is a stainless steel chamber. This here is a diode laser which is developed for instance, for telecommunication purposes. It is awfully robust. It has a lifetime of 100,000 hours or something. And everything can be done very robust. So this is the whole thing is lends itself to industrial applications and applications into hostile environment. This is pretty much what we have done since then. This was the first photoacoustic system. You see here what I told you that the acoustic chamber is a stainless steel block, and here is the holder for the diode laser. This is the electronics. So it is pretty straightforward. So what can you do with photoacoustics? For instance, you can try to detect water vapor in the upper atmosphere. Why would you do such thing? Climate research, of course. You know that we speak about very much about CO2. But of course, the problem with CO2 that it has a bad PR. Water vapor is much more important greenhouse gas, but somehow it has much better PR. So it is, we are not speaking about it, although this is the major source of greenhouse effects. Of course, you need you should know the distribution of water vapor if you want to improve your weather forecasting, especially severe weather. So when the thunderstorm cells are coming, if you know better the moisture around the surrounding region, then you can have a much better forecast. And of course, it was a relatively new, not that new development. This is the rare occasions when terroristic attacks help science, because the issue of contrail came up during September 11th, when the airspace of US was closed for 4 days. And people recognized that the daily temperature fluctuation has increased by a degree and a half, because there was no contrail at all. And then people started to simulate, and it turns out that yes, contrails do have an environmental effect. Actually, the contrails are even more important in their consequences than CO2 emissions. So people are speaking about how to decrease the CO2 emission of the aircraft, but contrail is much more important. This is the sky of Szeged. These are clouds that are actually created by a contrail. So this is the reason why you practically create by contrails high-lying cirrus clouds, which does not necessarily belong to that on the sky. And ironically, when you hear people telling you that, oh, in my time there was not so many contrails, then they are right, because the modern engines of aircraft generate easier contrail than the older ones. These are much more economic, but this is partially the reason why. So of course, it's actually okay. So there are some engineering tricks, the consequence of which that these new engines have a much better efficiency, but they are generating more case, we have developed measuring a water vapor measuring water acoustic system, which was a pretty tough job because, I mean, if you consider what to be measured, so when the plane is on the ground, then the water vapor concentration here in this room, it could be something like 40,000–50,000 ppms. When it in the upper atmosphere, in the cruising altitude, like 10 kilometers, then you have a temperature of -50 degrees, a pressure of 0.2 bars, and the concentration is like 3 ppms. So you have more than 4 orders of magnitude range that you have to measure. So it's not a very easy task, but we actually eventually could solve it, and then became part of a European project called Caribbean, which was, this is actually a cargo container, but you don't have luggage inside, but measuring devices. And this guy here is our water vapor measuring device, which has made quite a few successful flights. There was a sampling pipe outside. This was an airplane of Lufthansa, and there was an outside pipe sampling the air, and all these different devices were measuring different components in the higher atmosphere. Here is a Frankfurt-Osaka flight. That was a relatively early flight of the device. Actually, you can see here two curves. When the two curves, the blue and the green ones, are not running together, then there are clouds, because this is actually the water. I mean, this is actually the pipe, the sampling pipe had two inlets, one facing the flight direction, one is back, and if you compare the two inlets, then you can, for instance, see here that the light went through clouds. In any case, we have developed several other applications. One successful application for which we actually even founded a spin-off company called Highrays. The most successful product of Highrays was a device that was capable of measuring H2S in natural gas. This device has been sold to several places, among other things, offshore drilling platforms. The reason why I'm showing you this, because this is a tricky environment, because if your device is not giving the signal, then people may die, because H2S is highly poisonous. If it gives you a false alarm, then they will evacuate the platform. That is like $6 million per day if you do it, if it is a false alarm. So you better don't do false alarm, and your device is better working, because people's life might be at stake. In any case, this is exactly why we believe that the robustness of the technology is very well suited for applications in very harsh environments. Here is a new project. We actually developed a photoacoustic gas analyzer by which we measure methane in exhaled air, because methane is produced by your body under stress conditions. So methane is a good stress indicator, which could be triggered by physical activity, or this is a device in the operating room when the medical doctors are performing an open heart operation. It is quite important, because if you are making operation like this, then the many physiological parameters of the patient is practically controlled by the anesthesiologist. Your heartbeat, I mean, how much you want. The guy will set your heartbeat. oxygen saturation can also be controlled more or less by the doctors. Seemingly, the level of methane produced by your body cannot be controlled. It is really a reaction of the body, so that is the reason why our colleagues are saying that this could be quite a useful measurement. And then let's speak about what sometimes seems to be quite obvious, but not always that obvious. So, of course, you have aerosols in the atmosphere. You can nicely measure aerosols by a photoacoustic device. You can imagine, I was speaking about, up to now, we were speaking about molecules, water vapor, water molecule, H2S, methane, these are molecules. But for the light, it is absolutely immaterial whether the light is absorbed by a molecule or by a carbon particle. The same procedure will take place. You heat up the carbon particle and it gives the energy to the environment, and then you have the photoacoustic signal. So you can measure the photoacoustic signal generated by aerosols. Especially, photoacoustic technology has a very, very important advantage, that it is selectively sensitive towards highly absorbing species. So in cases when other methods are based on dry scattering, but a piece of dust scatters the light the same way as a carbon particle, but the carbon particle has a different absorption. So basically, for instance, if you are walking at the seashore, there is many small salt particles in the air, but you don't mind. You will say, oh fine, I had this nice fresh air at the sea. And it is really, it is not harming you. If you inhale a bit of salt, no problem. But if